For millennia, humanity looked at the night sky and assumed one fundamental truth: that the cosmos was a fixed, eternal, and unchanging stage, a clockwork mechanism of predictable orbits. Even Albert Einstein, when his own equations of general relativity predicted a dynamic, moving universe, refused to believe it. He invented a cosmological constant to force his math to conform to the static reality everyone assumed was true. He would later call this the single biggest blunder of his entire life. Because he was wrong. They were all wrong. The universe is not static, it is not eternal, and it is not unchanging. It is violently, relentlessly, and fundamentally expanding. This single fact, discovered less than a century ago, is the foundation of all modern cosmology. It is the key that unlocks our origin, our ultimate fate, and the very nature of reality itself. And it leads to a question so profound it borders on madness. If the universe is getting bigger every second, what is it expanding into? If you are ready to confront the true nature of reality and the scale of the cosmos we inhabit, hit that like button and subscribe. Prepare yourselves. Let's begin. The revolution began not with a grand theory, but with a simple, persistent observation. In the 1910s, an astronomer named Vesto Slipher, working at the Lowell Observatory in Arizona, began to meticulously study the light coming from strange, fuzzy patches in the sky, then known only as spiral nebulae. He used a spectrograph to split their light into a rainbow, looking for the chemical fingerprints of their composition. But he found something else, something impossible. The spectral lines of these nebulae were not where they were supposed to be. They were almost all shifted dramatically toward the red end of the spectrum. Slipher knew exactly what this meant. It was the Doppler effect, the same phenomenon that changes the pitch of a siren as it speeds past you. A shift to blue means an object is moving closer. A shift to red means it is moving away, and almost every nebula Slipher measured was rushing away from us at incredible speeds, some over 1 million miles per hour. The universe, it seemed, was running away from us. But this was just a collection of data points, a profound mystery without a framework. The prevailing wisdom, held by giants like Harlow Shapley, was that these nebulae were relatively small, nearby clouds of gas inside our own vast Milky Way. The universe was the Milky Way. There was nothing else. Enter Edwin Hubble, a charismatic, ambitious astronomer working with the most powerful tool on Earth, the new 100-inch Hooker telescope at Mount Wilson Observatory in California. Hubble was obsessed with one of the brightest of these spiral nebulae, Andromeda. He was hunting for novae, exploding stars, within it. In 1923, he found one, but as he compared his photographic plates, he realized it wasn't a nova. It was something far more important. It was a Cepheid variable. Cepheids are a special class of star. Their brightness pulses at a regular rate, and that rate is directly, mathematically, linked to their true intrinsic brightness. They are the universe's standard candles. By comparing how bright a Cepheid appears to how bright it must be, you can calculate its distance. Hubble did the math. The number he calculated was stunning. The Cepheid in Andromeda was nearly 1 million light-years away. This single calculation shattered our understanding of the cosmos. The Milky Way was not the universe. It was just one island universe, one galaxy among countless others. Andromeda was a galaxy in its own right, just as large as our own. The universe was suddenly, unimaginably vast. This discovery alone would have cemented Hubble's name in history. But he wasn't done. He had solved the first part of the puzzle. Now, he turned to the second. He began to apply his new distance measuring technique to other, more distant galaxies. And as he did, he combined his new distance data with Vesto Slipher's mysterious redshift measurements. A pattern emerged. It was not random. It was a perfect, linear, undeniable relationship. The farther away a galaxy was, the faster it was receding from us. This was not a random scattering of galaxies flying through space, like shrapnel from an explosion. This was something far more profound. It was a uniform expansion of space itself. The relationship became known as the Hubble law, and the number that governs it, the Hubble constant, is the measure of the universe's expansion rate. The data was inescapable. Every galaxy, in every direction one, was moving away from every other galaxy. It meant that in the past, everything must have been closer together. And if you run the clock all the way back, everything must have been compressed into a single, infinitely dense, infinitely hot point. This idea was not entirely new. Unknown to Hubble, a Belgian priest and physicist named Georges Lemaitre had already arrived at the same conclusion, not with a telescope, but with mathematics. Lemaitre was one of the first to take Einstein's equations of general relativity seriously. He saw that Einstein's blunder, the cosmological constant, was unnecessary. The equations naturally, beautifully, described a dynamic, expanding universe. In 1927, 2 years before Hubble published his famous paper, Lemaitre published his own, proposing that the universe was expanding and even calculating an expansion rate. He went further, postulating that this expansion must have originated from what he called a primeval atom, or the cosmic egg, a singular beginning for space and time. It was the first rigorous mathematical description of the Big Bang. At first, the scientific community, including Einstein, dismissed L's ideas. But then came Hubble's data. The observations from Mount Wilson were the physical proof. The debate was over. The static, eternal cosmos was dead. Our universe was born, and it has been expanding ever since. This discovery, this irrefutable proof, became the first pillar of modern cosmology. But a pillar is not a building. Proving the universe is expanding is one thing. Proving it began in a singular fiery creation event is another. For that, astronomers would need to find a ghost, an echo from the dawn of time, hiding in plain sight, filling all of space. The new reality of an expanding universe, born from Lemaitre's mathematics and proven by Hubble's telescope, cleaved the world of physics in two. On one side, the proponents of a beginning, a moment of creation. On the other, the steady-state theorists, led by the formidable Fred Hoyle, who found the idea of a singular origin philosophically repulsive. Hoyle proposed that the universe was indeed expanding, but that new matter was continuously, spontaneously created in the voids to keep the universe's density constant for all eternity. It was an elegant, if radical, idea. The expanding universe of Lemaitre and Hubble, which Hoyle derisively nicknamed the Big Bang, implied something testable. If the universe began in an infinitely hot, dense state, and has been expanding and cooling ever since, then the heat from that initial explosion, its afterglow, must still be here. It must be everywhere. In the 1940s, the physicist George Gamow and his colleagues, Ralph Alpher and Robert Herman, calculated exactly what this afterglow should look like. They predicted that the universe should be filled with a uniform bath of radiation, the ghost light of creation. cooled by 13.8 billion years of expansion to a frigid echo, just a few degrees above absolute zero. It was a staggering, testable prediction. And then, for 2 decades, nobody found it. The technology was almost there, but the search was not a priority. The debate between Big Bang and steady state remained a theoretical stalemate until 1964. At Bell Labs in Holmdel, New Jersey, 2 radio astronomers, Arno Penzias and Robert Wilson, were trying to calibrate a massive horn-shaped antenna. They were not looking for the beginning of time. They were trying to measure radio signals from the Milky Way. But they had a problem. A noise, a persistent, uniform, unavoidable hiss, coming from every single direction in the sky, at all times, day or night, season after season. It was not the Milky Way. It was not the sun. It was not radio interference from New York City. They even, in a now legendary move, climbed into the antenna and scrubbed it clean of a white dielectric material, otherwise known as pigeon droppings. The noise remained. It was a signal with a temperature of approximately 3 degrees Kelvin. They were completely stumped. Meanwhile, just a few miles away at Princeton University, a team of physicists led by Robert Dicke had independently re-derived Gamo's prediction. They were convinced the echo of the Big Bang was real, and they were actively building an instrument to find it. The moment of collision was pure chance. Penzias happened to call a colleague who mentioned Dicke's work. The 2 groups met. The instant the Princeton team heard about the 3-degree hiss Penzias and Wilson couldn't eliminate, they knew. They knew exactly what it was. Penzias and Wilson had not found noise. They had found the oldest, most profound signal in existence. They had found the afterglow of creation. This was the cosmic microwave background, the CMB. It was the definitive, irrefutable proof. The steady-state theory was dead. The universe did have a beginning. The Big Bang was not just a theory. It was an observable, measurable fact, its residual heat still warming the entire cosmos. This light is the oldest photograph possible, a snapshot of the universe when it was only 380,000 years old, the moment it first became transparent. And this photograph is nearly perfect. The CMB is astonishingly uniform. The temperature is 2.725 degrees Kelvin in every direction you look, to an accuracy of 1 part in 100,000. This near-perfect smoothness, this isotropy, is a profound clue. It tells us that in its infancy, the universe itself was almost perfectly uniform, a hot, homogeneous fog of plasma. But almost is the most important word in cosmology. When our instruments became sensitive enough, we found tiny, minuscule fluctuations in that temperature. Tiny patches of the fog that were infinitesimally hotter or colder. These are the seeds. These are the lumps in the primordial soup. The tiny gravitational imperfections that, over billions of years, would pull matter together. They are the reason you are here. Every star, every galaxy, every cluster of galaxies, every planet, and every living being is a direct descendant of those impossibly small imperfections in the echo of the Big Bang. We had found the proof of our origin, written in cold light across the entire sky. But this monumental discovery only deepened the central question. If the Big Bang was not an explosion in space, but the start of an expansion of space, what does that actually mean? The discovery of the cosmic microwave background cemented the Big Bang as the undisputed origin story of our universe. The echo of creation was found. The case was closed. But this victory immediately forced cosmology to confront a far more difficult, more abstract, and more profoundly unsettling question. The universe is expanding. Fine. But what precisely is expanding? The human mind, trained by billions of years of evolution in a world of projectiles and explosions, defaults to a simple, intuitive image. The Big Bang must have been an explosion, a cosmic grenade. We imagine a point of infinite density detonating in an empty, pre-existing void. We picture galaxies as pieces of shrapnel, flying outwards through this empty, static, three-dimensional stage. This is the image taught in classrooms, drawn in textbooks, and visualized in countless documentaries. It is sensible, it is intuitive, and it is catastrophically, fundamentally wrong. The galaxies are not moving through space. The redshift Hubble measured is not, in the strictest sense, a Doppler shift from objects racing away from a central point. The reality is infinitely stranger. The galaxies are, for the most part, standing still. They are standing still, but the space between them is growing. The very fabric of reality itself, the geometry of space-time, is stretching. This is the metric expansion of space, a core prediction of Einstein's general relativity. The simplest analogy, and the most effective, is one used by Lemaitre and Arthur Eddington themselves, a lump of dough rising in an oven. Imagine a loaf of raisin bread. The raisins are the galaxies. The dough is space. As the bread bakes, the dough expands, pushing all the raisins away from each other. From the perspective of any single raisin, all the other raisins are moving away. A raisin 2 inches away might move 1 inch farther in 10 minutes, but a raisin 4 inches away, with twice as much dough in between, will move 2 inches farther in the same amount of time. It appears to be moving twice as fast. This is the Hubble law, explained perfectly. The farther away a galaxy is, the more dough, the more space there is between us and it, and all that space is expanding. The cumulative stretch adds up, so the most distant galaxies appear to be receding at the fastest, most incredible speeds. This is not a metaphor. This is the mathematical reality. The light we observe from a distant galaxy, the light that Vesto Slipher and Edwin Hubble measured, is not red-shifted because the galaxy is flying away from us like a speeding ambulance. It is cosmologically red-shifted. As a photon of light travels for billions of years across the cosmos, the space-time it is traveling through is being stretched. The photon's own wavelength is stretched with it. The wave of light gets longer. Longer wavelengths of light are redder. The light didn't leave the galaxy red. It was stretched to red during its long, long journey across an expanding medium. This reframes the entire discovery. The redshift is not a measure of velocity through space. It is a measure of how much the universe itself has expanded since that light first began its journey. This immediately solves a major paradox. If the most distant galaxies we see were actually flying through space at the speeds their redshift implies, many would be moving faster than the speed of light, an apparent violation of Einstein's ultimate speed limit. But they are not. The galaxies are not moving faster than light. The expansion of space between us and them, a process not bound by the speed of light, is what creates the separation. The speed limit of light applies to objects within space-time, but not to the stretching of space-time itself. But this new understanding creates its own pressing question. If the very fabric of space is stretching, why aren't we stretching? Why isn't the Earth expanding, pulling away from the Sun? Why isn't the Milky Way being torn apart? Why isn't the ruler on your desk getting longer? Because the metric expansion is a global phenomenon, not a local one. It is a vast cosmic tide, but it is an incredibly gentle one. On the scales of atoms, planets, and even galaxies, the other fundamental forces are colossally more powerful. The electromagnetic and nuclear forces that hold your body together are quadrillions of times stronger than this expansion. The gravity binding the Earth to the Sun, or the Sun to the Milky Way, is magnitude stronger. These are gravitationally bound systems. They have detached from the cosmic flow. They have won the fight. The cosmic expansion only dominates in the vast, dark, empty gulfs between the great galaxy clusters. But this correct, anatomical understanding of expansion, this stretching fabric, only makes our initial question more urgent. It forces the intuition to scream. If the fabric is stretching, there must be something outside the fabric for it to stretch into. Why does our mind rebel so fiercely against the alternative? The problem is not your curiosity. The problem is your brain. The question, what is the universe expanding into, is not a foolish one. It is not born from ignorance. It is, perhaps, the most fundamental and inevitable question a conscious mind, one born from evolution on a three-dimensional planet, can possibly ask. It springs from the very wiring of our cognition. You are a modeling machine, a biological neural network trained by tens of millions of years of survival to understand a very specific and very limited set of rules. Earth physics. We throw rocks. We watch water fill a container. We see fire spread across a forest. We inflate a balloon, and it expands within the air of a room. Every single second of your life, your experience reinforces with absolute unyielding force one central axiom. All expansion requires an outside, a container, a pre-existing vacuum, an environment to be filled. Our brains do not have a category for an event that has no outside. It is a cognitive void. It is a syntax error in our mental software. And the name we gave this event is a spectacular act of self-sabotage. The Big Bang. It was coined by the astronomer Fred Hoyle as an insult, a way to mock an idea he despised. And yet, the name stuck, and with it, it planted an image in the global consciousness from which we may never recover. The image of a bomb, a cosmic grenade, an unimaginable explosion happening at one location, at one moment, detonating within a vast, dark, infinite, and pre-existing emptiness. This single image is the source of all the confusion. It forces us to ask, where was the center of the explosion? Where is the shrapnel wave? And most critically, what was the name of the arena where this bomb went off? This entire image, taught in schools and visualized in documentaries, is completely, catastrophically, and fundamentally wrong. Let's dismantle the center. If the universe exploded from a point, where is that point? Where is the cosmic ground zero? The answer is so profound, it is disorienting. There is no center. Or more accurately, everywhere is the center. The point of the Big Bang was not a tiny object floating in a void. The point was a state of infinite density and temperature. The entire universe, every cubic inch of the space you see, and the trillions of light years beyond it you will never see, was compressed into that state. The Big Bang did not happen over there, while we are over here. The Big Bang happened here. It happened in the exact point where you are sitting. It happened in the point where the Andromeda galaxy is now. The expansion we observe is not the sight of debris flying away from a central blast point. It is the uniform, metric expansion of the fabric of space itself, everywhere, all at once. Every galaxy sees all other galaxies receding from it. Every galaxy, therefore, has an equal claim to being the center of the universe. This is the ultimate fulfillment of the Copernican principle. We are not just on a mundane planet, in a mundane solar system. We are in a location that is, in every way, completely unspecial. There is no center because everywhere is the center. Now let's dismantle the before. This is the other failure of our intuition. If the Big Bang was the beginning, what came before it? Again, our mind, a machine of cause and effect, demands an answer. An engine must have a starter. But Einstein's general relativity tells us that space and time are not separate entities. They are a single, unified, four-dimensional fabric, space-time. Gravity is the curvature of this fabric. The Big Bang, then, was not just the beginning of matter and space. It was the beginning of time itself. To ask, what came before the Big Bang, is a logically incoherent question. It is a failure of our language. It is the semantic equivalent of standing at the geographic North Pole and asking, which way is north from here? There is no north of the North Pole. It is the point where the very concept of north begins. In the same way, there is no before the Big T Bang. It is the point where the very concept of before time itself begins. Trying to apply concepts like before or into to the Big Bang is like trying to use a screwdriver to measure temperature. They are the wrong tools for the job. This is where intuition dies. We are trapped in a cognitive dissonance. Our bodies are made of star stuff forged in an expansion, but our brains evolved to dodge predators on a savanna. Our survival software cannot process cosmic reality. The universe is not obligated to make sense to our primate minds. It is not required to conform to our terrestrial expectations. The universe simply is, and the laws that govern it, written not in words but in mathematics, describe a system that does not need an outside to exist. A system that can be finite, yet have no edge. A system that can expand, but not into anything. To understand this, we have to do what science does best. We must abandon our common sense. We must cast aside the intuition that served us so well on Earth and, instead, trust the only guide that has proven capable of navigating this impossible realm, the equations of relativity. And those equations, when solved, provide an answer that redefines the very nature of reality. The failure of our intuition is not the end of the story. It is the beginning of the journey. When our hardwired common sense shatters against the scale of the cosmos, we are forced to abandon it and trust the only tool that has ever successfully navigated this alien realm, mathematics. Specifically, the mathematics of Albert Einstein's general relativity. This is not just a syntax of equations. It is a new language. It is a framework for reality itself, one that describes the universe as a single, unified, four-dimensional object called space-time. And when you pose our question to this framework, it provides a direct, unambiguous, and profoundly counterintuitive answer. The reason we cannot find the outside that the universe is expanding into is because the outside does not exist. It is not required. The universe, according to Einstein, can be a complete self-contained system that expands without needing an external void to accommodate it. To grasp this, we must, once again, use an analogy. It is an analogy so famous, it has become a cliché. And yet, it is so profound, it is almost always misunderstood. The surface of an inflating balloon. Imagine you are a creature of pure two-dimensional existence, a flatlander ant, whose entire universe consists of the rubber skin of a balloon. You know only forward, backward, left, and right. The very concept of up or down, the third dimension, is a form of madness to you, a philosophical impossibility. Now, someone, somewhere, a being in this hypothetical 3D hyper-reality, begins to inflate the balloon. What do you, the 2D ant physicist, observe from within your 2D universe? You observe something miraculous. Every other point on the balloon surface appears to be moving away from you. The points closer to you move away slowly. The points on the far side of the balloon, with the most rubber between you and them, move away from you very, very fast. You have just, with your ant telescope, discovered Hubble's law. You would also discover something else. Your universe, the 2D surface, is clearly finite. There is only so much rubber, and yet it has no edge. You can set off in one direction, walking in a perfectly straight line, and you will never fall off. You will simply, after a very long journey, end up exactly back where you started, having circumnavigated your cosmos. Finally, your universe has no center on the surface. Every single ant on the balloon, no matter where it stands, sees the exact same thing. All other ants are receding. Every point is the center. This is a perfect, finite, self-contained, and expanding universe, all described in 2 dimensions. But here, precisely here, is where our 3D evolved intuition lays its catastrophic trap. We, as 3-dimensional beings, look at this analogy, and we see the outside. We see the 3D room the balloon is expanding into. We see the inside, where the air is coming from. Our brain screams, "Aha! Proof! Expansion must be into something." The 2D surface is expanding into the 3D room, so our 3D universe must be expanding into a 4D something. This is a failure of our privileged perspective. We are mistaking the analogy's container for a cosmic necessity. The true mind-breaking revelation of general relativity is that the outside, the 3D room in the analogy, the hypothetical 4D hyperspace in ours, is mathematically superfluous. It is not required. Einstein's equations describe the geometry of the balloon surface, its curvature, its expansion, as an intrinsic property of the surface itself. The 2D ant physicist can discover everything about its universe from within. It can draw a massive triangle, connecting 3 distant points, and measure the angles. On a flat 2D plane, the angles would add to 180 degrees. But on its curved, spherical surface, the angles will always add up to more than 180. It has just performed an intrinsic measurement. It has proven, without ever seeing or even conceiving of a 3rd dimension, that its universe is curved. It can measure the expansion rate, its Hubble constant, as an intrinsic stretching of its own 2D metric. The math works perfectly, entirely from within. We are that ant. Our 3D universe is the surface in this analogy. General relativity gives us the tools to measure our own universe's properties intrinsically. We can measure the expansion. We can measure the curvature. And the equations that describe this, the Friedmann equations, are entirely self-contained. They do not have a variable for what is it expanding into. The question itself becomes meaningless. The universe is not a 3D object moving through a 4D space. The universe is the 4D space-time manifold, and that manifold is changing. Its intrinsic geometry is stretching. The expansion is a change in the scale of the universe itself, not a movement into something else. This is the standard answer. This is the textbook solution. A universe that is finite or infinite, but in either case, needs no outside. It is a reality that is complete, self-contained, and expanding on its own terms. But this entire answer, this whole framework, hinges on one enormous, unknown variable. The balloon surface was a sphere. What is the actual measured shape of our universe? Einstein's mathematics didn't just give us a philosophical answer. It gave us a testable prediction. It provided a direct physical link between the stuff in the universe and the shape of the universe. According to general relativity, density is geometry. The total amount of matter and energy per unit volume determines the ultimate curvature of space-time. This means our question about the outside is inextricably linked to the universe's ultimate fate and its overall shape. And it presented us with three, and only three, possibilities. The entire cosmic drama hinges on a single number, a parameter called omega. Omega is the ratio of the actual density of the universe to the critical density, the exact knife-edge amount of stuff required to make the universe perfectly flat. First, if omega is greater than 1, if the universe is denser than the critical value, then space-time is positively curved. It curves back on itself like the 2D surface of our balloon. This is a closed universe. In this scenario, the universe is finite, but just like the balloon surface, it has no edge and no center. If you were to fly a spaceship in one direction, you would, after an unimaginable amount of time, end up right back where you started. The gravity of all this matter would be so strong that, eventually, it would halt the expansion and reverse it, pulling everything back together in a catastrophic, fiery end time known as the Big Crunch. Second, if omega is less than 1, if the universe is less dense than the critical value, then space-time is negatively curved. It is shaped not like a sphere, but like a saddle or a Pringle chip. This is an open universe. In this geometry, parallel lines diverge. The angles of a triangle add up to less than 180 degrees. This universe is, by definition, infinite. It will expand forever, its thin spread matter never having enough gravitational pull to stop the expansion. It is a one-way trip to a cold, dark, empty eternity. Third, if omega is exactly equal to 1, if the universe, by some miracle, contains the precise amount of matter and energy to balance on this mathematical razor's edge, then the universe is flat. Its geometry is the Euclidean geometry you learned in school. Parallel lines remain parallel forever. The angles of a triangle add up to exactly 180 degrees. A flat universe, like the open one, is also most simply interpreted as being infinite. It too expands forever, though the expansion would, in a universe without dark energy, decelerate, coasting towards a stop, but never quite reaching it. For decades, this was the central quest of cosmology, to measure omega, to discover our geometry and thus our destiny. But how? How do you measure the shape of the entire cosmos from within? The answer is beautifully simple. You do exactly what the 2D ant physicist did in our analogy. You draw a triangle, the biggest triangle in the universe, and you measure its angles. We have a perfect ruler for this experiment. It is the cosmic microwave background, the echo of the Big Bang we discovered in Block 2. When we look at the CMB, we see those tiny, minuscule temperature fluctuations, the seeds of galaxies. We can calculate, from our understanding of physics, how physically large those hot and cold spots were when the light first began its journey 380,000 years after the Big Bang. We know the base of our triangle. The two legs of the triangle are the beams of light traveling from either side of that spot for 13.8 billion years to finally enter our telescopes, like the WMAP or the Planck satellite. The angle we measure is how large that spot appears to us in the sky. If the universe is closed and spherical, it would act like a magnifying lens, and the spots would appear larger than we expect. If the universe is open and saddle-shaped, it would demagnify the light, and the spots would appear smaller. If the universe is flat, the light would travel in perfectly straight lines, and the spots would appear exactly the size our physics predicts. The results are in. The data is unambiguous. The Planck satellite measured these angles with such precision that the answer is undeniable. The angles add up to 180 degrees. The spots are exactly the size they should be. To a margin of error of less than 0.4%, the universe is flat. This is one of the most profound and baffling discoveries in all of human history. We live in a universe that is balanced on the knife edge. The density, against all odds, is precisely the critical density. But it's the implication of this flatness that changes our core question. The simplest, most direct interpretation of a flat universe is that it is infinite. We are not just living in an expanding universe. We are living in an infinitely large expanding universe. And this makes our title question: what is it expanding into? Shatter in a new and more profound way. You cannot expand into something if you already are everything. An infinite, flat, stretching fabric of space-time does not need a container. It does not need a beyond. It simply is. It is an infinity getting bigger. But this profound answer that we live in an infinite, flat cosmos was about to be challenged by a new observation, a new force, a discovery so shocking it would tear up all our assumptions about density, fate, and the very engine driving the expansion. The flat geometry of the cosmos, confirmed by our most precise instruments, is a staggering revelation. It implies we live in a universe that is mathematically simple, balanced on a perfect knife edge. But the simplest, most direct interpretation of flatness is infinity. An infinite Euclidean space, stretching in all directions, forever. This is the new, profound reality. But this answer immediately creates a new, screaming contradiction. Because in every documentary, every textbook, and every science article, we are given a number. We are told, with great confidence, that the universe is 93 billion light-years across. This is a number. This is a diameter. This is a finite size. How can the universe be both flat and infinite, and also 93 billion light-years wide? Is this a mistake? A paradox? No. This is the difference between reality and what we are allowed to see. The total universe, the grand what is, may indeed stretch on forever. But we are creatures bound by inescapable laws. We are bound by the finite speed of light, and we are bound by the finite age of the cosmos. The universe has only been in existence for 13.8 billion years. This means there is a past horizon, a maximum distance from which light, traveling at 299,792,458 meters per second, has had time to reach us since the very beginning. This sphere of information, this bubble of perception, is our observable universe. It is not a physical wall. It is not an edge. It is not a boundary of stuff. It is a horizon of time and light. It is the only part of the universe that is, or ever will be, accessible to us. But this is where the number gets confusing. If the universe is 13.8 billion years old, why isn't this observable bubble 13.8 billion light years across? Or, if you account for two directions, 27.6 billion. This is the most common mistake in all of cosmology. The 93 billion light-year number is the answer to this puzzle, and the key, once again, is expansion. Imagine, right at the edge of our vision, we see a galaxy. The light from that galaxy has traveled for almost 13.8 billion years to reach our telescopes. But when that light began its journey, that galaxy was not 13.8 billion light years away. It was much closer. In the 13.8 billion years that its light was flying towards us, the universe itself, the fabric of space between us and that galaxy, was stretching. The galaxy was being carried away from us by this expansion, even as its light was racing to close the gap. It's like trying to walk up an escalator that is moving faster and faster. The light particle struggles against the expanding tide. The result is that the galaxy, whose ancient light we see today, is no longer 13.8 billion light years away. Its current position, its comoving distance, after 13.8 billion years of expansion, is now a staggering 46.5 billion light years away. It is a ghost. We are seeing the light from a place we can no longer, even in theory, ever reach. This is true in every direction we look. This creates a sphere of observation, a light bubble, with us at the center, and a radius of 46.5 billion light years. The diameter of this sphere, our total observable universe, is therefore 93 billion light years. This number is not the size of the universe. It is the size of our universe. It is the diameter of our jail cell, a cell whose walls are not made of brick, but of space-time and light. So what is at that edge? What happens at the 46.5 billion light-year mark? A wall, a sign, a void. The answer is as profound as it is terrifying. Nothing. Absolutely nothing. It is just a random point in space, no different from any other. If you were instantly transported to an alien astronomer in a galaxy on the very edge of our observable universe, their reality would be identical to ours. They would look up, and they would be at the center of their own 93 billion light-year observable bubble. They would look back in our direction, and we would be the impossibly distant ghost on the edge of their vision. And they would look 46.5 billion light-years in the other direction, into a vast new sphere of cosmos, a whole new universe that we are and will forever be completely blind to. This is the ultimate cosmic humility. If the flat, infinite model is correct, then what lies beyond our horizon is simply more universe, more galaxies, more clusters, more voids, more bubbles of observation, more 93 billion light-year patches of reality, tiled together in an infinite cosmic mosaic, an infinite number of universes, all inaccessible to each other, each one convinced it is the true center of creation. We are locked inside a single frame of a film that is infinitely long. This revelation is our new reality. Our horizon of knowledge is finite, but this entire calculation, the 93 billion light-year number itself, was based on one simple assumption, that we knew how the universe was expanding. For decades, we assumed the expansion was slowing down, pulled back by the gravity of all the matter within it. In the 1990s, two teams of astronomers set out to measure that deceleration, but they didn't find it. They found something else, something impossible, a new force, a new darkness that was about to tear up our entire understanding of the cosmos and its ultimate fate. The universe was flat. The data from the cosmic microwave background was irrefutable, and a flat universe, balanced on that perfect Euclidean knife edge, had one enormous glaring problem. All the stuff we could see, the galaxies, the stars, the gas, the dust, plus all the invisible, dark matter we knew must be there holding those galaxies together. All of it added up to almost nothing. It accounted for, at best, 30% of the critical density needed to make the universe flat. The math was broken. We were missing 70% of the entire universe. Where was it? This was the missing energy problem, and it was a catastrophe for cosmology. The geometry was flat, but the inventory was empty. Something was wrong. At the exact same time, in the 1990s, two independent teams of astronomers were locked in a fierce race to solve a different problem. Their quest was to measure the past of the expansion, to look back in time and clock the precise rate at which the universe was slowing down. This was a foregone conclusion. The universe is full of matter, and matter has gravity. Gravity pulls. Therefore, the expansion must be decelerating, held back by the collective gravitational pull of every galaxy, every star, and every speck of dust. The only question was how much it was slowing. Their tool for this measurement was not the CMB. It was something far more violent, an exploding star, specifically a Type 1a supernova. These are not just any explosions. A Type 1a supernova is a thermonuclear bomb with a standard fuse. It only happens when a white dwarf star, a dead stellar core, steals just enough matter from a companion star to reach a precise critical mass, the Chandrasekhar limit, 1.44 times the mass of our Sun. At that exact point, it begins, and the entire star detonates in an explosion of unimaginable and, more importantly, predictable brightness. They are standard candles because we know their true, intrinsic luminosity. We can see how dim they appear and calculate, with stunning precision, how far away they are. The two teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, embarked on a brutal, meticulous search. They would find these distant explosions, measure their redshift, their speed of recession, and measure their dimness, their distance. The prediction was simple. If the universe was decelerating, the very distant supernovae, the ones whose light had traveled for billions of years, should appear brighter than their redshift would imply. Why? Because their redshift tells us the current expansion rate. But if the universe was expanding faster in the past, before deceleration, then that supernova didn't have to travel as far to reach us. It would be closer, and therefore, it would look brighter. The team set out to measure how much brighter, but that is not what they found. The data came in, a trickle, then a flood, and it made no sense. It was impossible. The numbers were wrong. They checked their calculations. They recalibrated. They panicked, assuming some vast, embarrassing error, some cloud of cosmic dust they had failed to account for. But the data held. The most distant supernovae were not brighter than expected. They were dimmer. They were dimmer. They were consistently, undeniably, 10 to 15% dimmer than they had any right to be. This was not a subtle error. This was a cosmic revolution. The only possible interpretation, the one that made the team sick to their stomachs, was that these supernovae were farther away than all our models predicted. And the only way for them to be farther away is if the expansion of the universe had not slowed down. It had, in the last 6 billion years, sped up. This was madness. It was as if you threw a ball into the air, and instead of slowing down and falling back, it suddenly, halfway up, ignited a rocket and shot away from you into space. It violated everything we thought we knew. But the data from both teams, who had worked in secret, cross-checked and confirmed the result. It was real. In 1998, the world was told, the expansion of the universe is accelerating. This discovery tore the field of cosmology apart and rebuilt it from the ground up. It won Perlmutter, Schmidt, and Rees the Nobel Prize. And it solved, with terrifying elegance, the mystery of the missing 70%. The universe is flat, but 30% of its density is matter and dark matter. The other 70%, the dominant component of our entire cosmos, is this anti-gravity force, this energy of the void itself, pushing space-time apart. They gave it a name, a placeholder for our total, profound ignorance. They called it dark energy, the accelerating universe. This discovery was not just a correction, it was a complete rewrite of our cosmic inventor. Tori, before 1998, we thought we were just missing 90% of the matter in the universe, a problem we called dark matter. That was a big enough mystery. But the discovery of acceleration was infinitely more profound. It meant we were missing 70% of the entire energy density budget of the cosmos. And this missing 70% was not just a passive, invisible mass. It was an active, repulsive force. It is the engine. It is the dominant component of reality. And we have absolutely no idea what it is. The leading and perhaps most terrifying candidate is an idea that Albert Einstein himself proposed, and then famously renounced as his biggest blunder. It is the cosmological constant. In Greek, lambda. This is not a force in the traditional sense. It is not a field. It is the cost of the void. It is the fundamental energy of space-time itself. Our modern understanding of quantum mechanics, a theory that has been proven correct to astonishing precision, demands that the vacuum is not empty. It is not a quiet, still, black nothing. It is a roiling, chaotic, violent sea of potential. It is a quantum foam where virtual particles, pairs of matter and antimatter, are constantly, furiously, winking into existence and annihilating each other in timescales too small to comprehend. This is not just a theory. This zero-point energy is real. It has been measured in the lab via the Casimir effect, where two perfectly flat plates in a vacuum are pushed together by the pressure of the virtual particles outside them. The vacuum, it turns out, has energy, and according to general relativity, all energy has gravity. But this strange foundational energy of the void has a bizarre property. It has a negative pressure. It is a repulsive anti-gravity. It is a push. And because it is a property of space itself, it is constant. As the universe expands and more space is created, this new space brings with it its own identical vacuum energy. More space equals more push. More push equals more expansion. More expansion equals more space. This is a runaway feedback loop. This is acceleration. It is the perfect, elegant, simple explanation for everything we see. It fits the supernova data. It fits the flat geometry. Einstein's blunder wasn't a blunder at all. It was the key to the entire cosmos. There is just one problem. One tiny, insignificant catch. When our quantum physicists, using their most successful, most precise equations, sit down and calculate how much energy the vacuum should have, the number they get is a catastrophe. The value they calculate is 10,120 dollars. 1, followed by 120 zeros. That is the predicted energy density. The value we observe from the supernova data, the value of dark energy, is 1. This is not a small error. This is not a rounding issue. This is the single worst, most embarrassing, most profound failure in the history of physics. It is a discrepancy of 120 orders of magnitude. It is like measuring the diameter of a single atom and calculating it to be the size of the entire observable universe. It is a sign that our two greatest theories, quantum mechanics and general relativity, are fundamentally, violently, and completely incompatible. This catastrophe has forced physicists to look for an alternative. If dark energy is not the constant, unchanging energy of the vacuum, what if it's something else? This is the second candidate, known as quintessence. This is not a property of space, but a new thing in space. It is a fifth fundamental force, a dynamic, invisible, time-varying field, like a magnetic field that permeates all of reality. Unlike the cosmological constant, this field is not constant. It can change. It can evolve. It's like a ball rolling down a very long, very shallow hill. In the early universe, when matter and gravity were king, this field was dormant, holding its potential energy. But as the universe expanded and matter thinned out, this field woke up. It began to roll, and as it rolled, it converted its potential energy into this repulsive negative pressure, beginning the acceleration. This idea is attractive because it might solve another deeply unsettling philosophical problem: the cosmic coincidence. Why now? For the first 7 billion years of cosmic history, gravity was winning. The expansion was slowing down. For the next trillion years of the future, dark energy will be so dominant that all other galaxies will be pushed out of our sight. We just so happen to be alive in the one fleeting transitional eon where the density of matter and the density of dark energy are even remotely close to each other. We are alive at the precise moment of the cosmic handover. This feels special, too special. It violates the Copernican principle that we are not in a privileged place or time. A constant, unchanging vacuum energy offers no explanation for this coincidence. It's just dumb luck. But quintessence, a dynamic field, could. It could be that its trigger was caused by the universe reaching its current, thinned-out density. We aren't lucky. We are a consequence. We are 95% ignorant. Dark matter and dark energy make up the vast majority of our reality, and the engine driving it all is either the most profound proof that our theories are correct, or the most catastrophic evidence that they are completely, fundamentally wrong. The standard answer is clean, but for many, unsatisfying. The universe is flat, infinite, and expanding. It needs no outside. It is a self-contained, self-governing system. This is the cosmology of the textbook, the cosmology of Einstein's equations. But the discovery of dark energy and the catastrophic vacuum catastrophe it revealed, that discrepancy of 1 followed by 120 zeros, has become a profound crack in this beautiful, simple facade. This failure, the worst in the history of physics, is so complete that it has forced a new generation of theorists to ask a forbidden question. What if the standard answer is wrong? What if our intuition wasn't wrong? What if, in a way we could never have imagined, there is an outside? This is not a return to old-fashioned intuition. This is a journey into the most advanced, most speculative, and most mind-bending mathematics ever conceived. String theory. String theory, in its modern incarnation known as M-theory, is a candidate for the theory of everything. It is a framework that attempts to unite the two pillars of physics, general relativity and quantum mechanics, that so famously and disastrously failed to cooperate. It does this by making a radical, untestable, and mathematically beautiful proposal that at the core of all matter and all forces are not particles, but tiny, vibrating one-dimensional strings. But for the math of these strings to work, to create the gravity, the light, the electrons, and all the forces we see, they must vibrate in more dimensions than we know. Not just up, down, left, right, and forward, back. Not just time. M-theory, in its full form, requires 11 dimensions, 7 extra spatial dimensions, all curled up, hidden, and inaccessible to us at scales smaller than an atom. This is where the new cosmology begins. In this framework, our entire, vast, three-dimensional universe, this fabric of space-time that we call reality, is not the whole of reality. It is a four-dimensional, three-space plus one-time membrane, or brain for short. We are flatlanders in a cosmic sense. We are ants living on a 4D sheet, floating in a vast, higher dimensional, 11-dimensional hyperspace. This hyperspace, this grander, larger reality, is called the bulk. Suddenly, the title of this entire journey has a literal, physical, and mathematically rigorous answer. What is the universe expanding into? Nothing. What is the universe expanding in? It is expanding in the bulk. Our 4D universe is like a bubble of soap, and its expansion is the surface of that bubble stretching. But the entire bubble itself is floating in the 11-dimensional air of the bulk. This isn't just a change of scenery. This framework offers a completely new origin story, a rival to the Big Bang. In the ekpyrotic or colliding brains model, the Big Bang was not the beginning of time. It was not a singularity. It was a collision. In this model, our brain universe is not alone in the bulk. There are other brains, parallel to our own, floating through the 11-dimensional void. The Big Bang in this scenario was the day our brain crashed into another one. The colossal kinetic energy of this cosmic higher dimensional impact was converted into the matter, energy, and radiation that fills our universe, heating up our brain and setting its expansion in motion. The expansion we see is the rebound from this titanic clap of cosmic thunder. And dark energy? That acceleration. It could be the lingering, gentle, repulsive force between our brain and that shadow brain, as they slowly, after their collision, begin to drift apart again. But there is another, equally profound, multiverse model. This one, eternal inflation, does not come from string theory, but from the standard Big Bang model itself. It is a consequence of inflation, the theory that in the first fraction of a second of its life, a moment so brief it is written as a decimal point, followed by 31 zeros and a 1. The universe underwent a period of hyper-exponential expansion, faster than light, doubling in size over and over, driven by a powerful inflaton field. The theory of eternal inflation states that, in most of reality, a vast metaverse, this inflationary field never stops. It is a chaotic, eternal, self-reproducing foam, inflating at a godlike rate forever. But by sheer quantum chance, in some tiny random patches, this field can decay. It can cool, and its energy can be released, creating a pocket or bubble universe. In this model, our entire 93 billion light-year observable universe is not the universe. It is one bubble, an infinitesimal speck of calm in an infinite, raging ocean of inflation. And in that ocean, new bubbles, new universes, are being nucleated every single second. Each bubble would be born with its own random, physical laws. One bubble might have weak gravity and be stillborn. Another might have 12 dimensions and no electrons. Another, by sheer chance, would have the exact laws, the exact balance of forces, like ours, needed for stars, planets, and life to form. In this model, what is our universe expanding into has a new answer. It is expanding, stretching its own space-time within its own bubble. But the entire bubble itself is being carried away, like a speck of sea spray in a hurricane, by the eternal self-reproducing inflation of the metaverse outside. We are either a sheet of paper in a library of 11 dimensions, or a single bubble in an infinite cosmic foam. In both, the answer is the same. Our reality is not all of reality, and our expansion, which for so long seemed a local affair, is now tied to a fate and a future that is infinitely larger and infinitely stranger than we ever dared to imagine. The universe is expanding, the fabric of space is stretching, and this expansion is accelerating, driven by a repulsive, dominant, and utterly mysterious dark energy that now makes up 70% of reality. We have followed this mystery from Hubble's telescope to the farthest, most speculative realms of M-theory. We have asked what is expanding, how it is expanding, and even explored the possibility of what it is expanding in. But this journey has avoided the final and most human question of all. Where is this taking us? We know our origin, the Big Bang. But what now is our destiny? The answer, dictated by that same dark energy, splits into two paths. One is an eternity of cold solitude. The other is a moment of total universal annihilation. The first, and most likely scenario, is called the Big Freeze, or the heat death of the universe. This is our fate if dark energy is a true, unchanging cosmological constant. If it is, as we suspect, the simple, unyielding energy of the vacuum itself. In this future, the push of expansion remains constant, but its effect is cumulative. The runaway feedback loop we discovered, more space, more dark energy, more expansion, continues forever. The implications are not immediate. They are slow, profound, and utterly terrifying. The first thing to happen is that, one by one, the other galaxies in the night sky will wink out. This is not a metaphor. As the universe accelerates, Distant galaxy clusters are being pushed away from us at ever-increasing speeds. Soon, they will cross a cosmic event horizon. This is a point of no return. It is the point at which they are receding from us faster than the speed of light. The light they emit, even as it travels towards us at light speed, is being pulled away by an expansion of space so vast that it can never, ever bridge the gap. The light is redshifted into oblivion. The galaxies don't die. They are simply erased from our sky. They are locked forever beyond our observable universe. Over the next 100 billion years, our night sky will be rendered barren. The Virgo supercluster, the Coma cluster, all the beautiful swirling islands of light, all will vanish. The only thing left in our sky will be the members of our own gravitationally bound local group. This small collection of galaxies, including the Milky Way and Andromeda, will not be torn apart. Their mutual gravity is strong enough to overpower the dark energy. They will, in fact, collide and merge, forming one single gargantuan supergalaxy, Milkomeda. For the rest of eternity, this will be our new universe, an island of matter, a single supergalaxy floating, utterly and completely alone, in an infinite, black, and accelerating void. This is not the end. It is the beginning of the end. From here, the laws of thermodynamics take over. For 100 trillion years, this galaxy will live. Stars will be born. They will die. They will recycle their dust. But eventually, the gas will be used up. The last red dwarf stars, the final faint embers of creation, will gutter and die. The universe will become a graveyard of cold, dead stellar remnants, black holes, neutron stars, and white dwarfs. For quadrillions of years, even these will decay. Planets will be flung from their dead stars. The galaxy itself will dissolve, its components drifting apart. Protons themselves may decay, and the black holes, the last beacons of mass, will slowly, agonizingly evaporate over a timescale so vast it is called a googol of years, a 1 followed by 100 zeros. The end state is a heat death, a universe that has expanded so much and for so long that it is just a thin, cold, infinitely vast soup of stray photons, neutrinos, and fundamental particles, with a temperature that approaches, but never quite reaches, absolute zero. It is the end of heat, of light, of information, and of time. But what if dark energy is not constant? What if it is quintessence, and its energy is increasing over time? This is the second scenario. This is the Big Rip. In this future, the anti-gravity of dark energy grows stronger, second by second. For now, it is weak. But in this model, a countdown begins. As the push grows, it begins to systematically dismantle the universe, from the largest structures to the smallest. With about 1 billion years to go, the rip begins. The dark energy push becomes stronger than the gravity-binding galaxy clusters. The Virgo supercluster, our cosmic neighborhood, is torn apart. With 60 million years to go, the push becomes stronger than the gravity holding our galaxy together. Milkomeda is violently, unceremoniously unbound. The stars are flung into the dark. With 3 months to go, the push is stronger than the gravity holding our solar system. The Earth is torn from its orbit, cast loose into the expanding chaos. With 30 minutes to go, the Earth itself, now a frozen rogue planet, is ripped apart. The push is now stronger than the planet's own gravity. With 1 second to go, the push is stronger than the electromagnetic force holding you together. your atoms are pulled apart. And then, at the final moment, in the last billionth of a trillionth of a second before the end, the dark energy becomes infinitely strong. It is now more powerful than the strong nuclear force. The nuclei of atoms themselves are ripped apart. The push becomes a singularity, tearing the very metric, the very fabric of space-time itself, into an infinite number of disconnected pieces. Freeze or rip. An eternity of cold or a moment of fire. This is the destiny written for us by the darkness. This leaves us with only one final question. Why does any of this matter? We began this journey with a single question. A question born from an intuition so deep, so human. It feels like a law of nature. What is the universe expanding into? We expected an answer. A place, a name, a void, a hyperspace. And instead, we found something infinitely more profound. We found that the question itself was a mirror. It was our terrestrial, three-dimensional, evolutionary forged mind staring into the abyss, and the abyss staring back, telling us, "You are thinking too small." The answer was not a place. The answer was a process. The answer was time. The answer was geometry. The answer was a recalibration of our entire place in existence. We did not find a comfortable answer. We found the truth. We discovered that we live in a universe not of simple, mechanical certainty, but of profound, dynamic, and terrifying mystery. We traded a small, static, eternal cosmos for a reality that is vast, accelerating, and 95% unknown. We learned that the common sense that built our civilizations, that taught us to hunt and to build, is a local bylaw. It is a set of survival tools, and it fails catastrophically when faced with the scale of the real. We discovered that our entire reality, every atom in our bodies, every galaxy in our sky, is just 5% of the total. The rest is a dark symphony of matter we cannot see and an energy we cannot comprehend. This is not a failure. It is the greatest discovery of all. It is the revelation that we are not at the end of physics. We are not staring at a finished map. We have just, for the first time, stepped off the boat and realized that the tiny island we knew is not the world. An entire, vast, dark continent lies waiting. This is the so what. This is why it matters. It matters because this journey, this relentless human quest to understand, is the single most defining characteristic of our species. We are the universe, made briefly, accidentally, conscious. We are a collection of star stuff, animated by chance, that has evolved the capacity to look back at the source, at the inferno of the Big Bang and the cold darkness of the future, and ask. The cosmos did not create us to be a passive audience. We are the cosmos, in the act of self-examination. The expansion is not something that is happening to us. It is the reason we are here. The expansion itself, the stretching of space-time, thinned the primordial fire, allowing it to cool, to congeal, to form matter. It created the distances that allowed galaxies to form in peace, instead of collapsing back into a single gravitational singularity. The cosmic expansion is our let there be light. And what of the end? What of the big freeze or the big rip? What is the meaning if it all ends in a cold, dark void or a violent, tearing annihilation? This is the final and most human revelation. The universe, in its grand, indifferent, mathematical beauty, does not promise us forever. It offers us something far more precious. It offers us now. We are alive in the cosmic handover, the one fleeting, magnificent eon where the sky is not empty. We are alive in the brief window after the fire, but before the ice. We can look up and see the evidence, the distant light of our cosmic cousins in Andromeda, in the Virgo supercluster. 1 trillion years from now, our Milkomeda descendants will look up into a black, featureless void, their history erased by the accelerating expansion. They will have no way of knowing about the Big Bang. They will be alone, an island of light in an infinite, unknowable darkness, with no past and no context. We are the lucky ones. We are the generation that gets to see the truth. To ask, what is the universe expanding into, is the wrong question. The right question is, what does it mean to be a thinking, feeling being inside an expansion? It means that meaning is not something given to us by the universe. It is something we, the conscious part of the cosmos, create. The universe may be indifferent, but we are not. We are the ones who feel awe. We are the ones who see beauty in the mathematics of a dying star. We are the ones who, faced with an infinite, accelerating void, choose to build, to love, to explore, and to understand. We are the brief, brilliant, beautiful pattern that existence has woven before the pattern fades. The universe is expanding, and we, in our brief, glorious moment, are the ones who get to watch. We are the ones who get to know.